Welcome back to our series on probability. In this video, we will look at a classic result presented in the form of the following problem. If a couple makes the decision to keep having children until they have the same number of boys as girls, how many children do they expect to have? This question is obviously theoretical. We are assuming that this couple could have an unbounded number of children. If you find yourself uneasy with this assumption, and as a parent myself, I can think of few things more terrifying than you can think of it in the context of random walks. If you start at the origin of the number line, and each second you step either left or right randomly, how long do you expect it to take to get back to the origin? To keep things fun and borderline nightmarish, let's work within the context of children. We'll start by doing our usual thing of trying to nab an estimate without breaking a sweat. There are 4 ways for a couple to reach 2 children. Boy then boy, boy then girl, girl then boy, girl then girl. We can see that there is a 50% chance that the couple have reached parity at 2 children. That is, they will have the same number of each. What if, at the point of 2 children, they have had 2 of the same? From here, to break even by the time they get to 4 children, they need a very specific sequence. Randomness needs to work quite hard. If they've started with 2 girls, they will need 2 boys. If they've started with 2 boys, they will need 2 girls. The probability of such a precise sequence in either case is 1/4, and so it is clear that the chance of first achieving parity at 4 children is 1/2 times 1/4, which is 1/8. What if the couple has not achieved parity at this point? The chance of this is 3/8, and they will either have 1 boy and 3 girls, 1 girl and 3 boys, all boys or all girls. In these later 2 scenarios, it is impossible to get back to parity by 6 kids, and exceptionally hard to get back to parity by 8. I don't feel like we are actually getting close to an estimate, but we are developing an intuition for how hard it is to achieve parity once we step away from it. Potentially then, it feels like any estimate we get is going to be quite large. Some of you might actually know the answer to this problem. It's infinity. This might seem counterintuitive, but together, let's correct our intuition by proving it. We want to know the expected value of x, where x is the number of children where the couple has first reached parity. We can write down our usual formula for expected value. Here, P of x equals c is the probability that we first reach parity at c children. Clearly, c must be a positive even number, so we can write c equals 2k for some positive integer k. Now, all we need to do is figure out the probabilities, put them in that sum, and evaluate. As you know, I like to illustrate the structure through an example and leave the rest for you to do on a Friday night. So let's look at the case k equals 5. Here, we are trying to calculate the probability that parity is achieved for the first time at 10 children, that is, 5 boys and 5 girls. We can visualize this process as a random walk on this grid. We start at the point 0, 0. Whenever the couple have a boy, we move 1 to the right. Whenever the couple have a girl, we move 1 up. Then, the number of children it takes to achieve parity is just the number of steps it takes to touch this diagonal for the first time, excluding, of course, the starting point. For k equals 5, we want to count the number of ways that you can start at 0, 0 and end up at 5, 5 without touching the diagonal between these 2 points. Then, once we have counted these, to get a probability, we need to divide by 2 to the power of 10, as this is the total of all possible sequences of 10 children. Let's first look at the scenario where the first child is a boy. That is, our first step is from 0, 0 to 1, 0. Note that any subsequent path which first touches the diagonal at 5, 5 must eventually hit the point 5, 4 and then finish with a single upward step. As such, the problem reduces to counting paths in this subsquare, where we actually are allowed to touch but not go above the new diagonal. We've got a new subproblem. How many ways can one go from the bottom left of a square grid to the top right of a square grid when you are allowed to touch but not go above the diagonal? These are precisely the Catalan numbers. In general, for an n by n grid using only steps to the right and up, and without going above the diagonal, the number of possible paths is equal to the nth Catalan number. There are some videos out there that give some really nice proofs of this fact, so I'm going to task you with checking some of them out. This pre-established fact helps us to count the paths in our original square. The number of paths that take us from 10 to 54 is just the fourth Catalan number, and we can see that this is equal to 14. As the first and last move are both forced, the total number of paths is 14. Though we have to remember that we have only counted the paths that start with a step to the right. We need to also count the paths that start with a step up and first touch the diagonal at 5, 5. By symmetry, that most frequent of time savers, there are 14 of these also. So there are 28 paths in total. To convert to a probability, we need to divide by the total number of 10-child sequences. This gives us that the probability that x equals 10 is 28 over 1024. I think that we've worked through the k equals 5 example carefully enough that we should have some confidence in generalizing. For k equals 5, the probability is equal to twice the fourth Catalan number divided by 2 to the power of 10. For general k, the probability is equal to twice the Catalan number for k minus 1 divided by 2 to the power of 2k. We can directly sub this in and give the resulting expression a small jiggle. Now we can go ahead and attempt to compute the expected value of x. We can throw in the exact form of the probability and then make some small algebraic manipulations to tidy things up. We can also re-index the sum to make it look a bit friendlier. We do this by substituting n for k minus 1. This is looking a lot simpler. And some of you will be onto this now. There is a really nice thing we can do to connect the two objects in the above sum. The two objects being 4 to the power of n and the binomial coefficient 2n choose n. We note that 4 to the power of n is equal to 1 plus 1 all to the power of 2n, and then apply the binomial theorem to get this expression. On the right-hand side, we have a sum of binomial coefficients. There are 2n plus 1 of them in total, and the largest one is the middle coefficient, 2n choose n. This should make sense. Each row of Pascal's triangle peaks in the center. This allows us to bound the sum from above by 2n plus 1 times 2n choose n. Rearranging this, we get a simple lower bound for the thing we are summing in our expected value. And we can plug this directly into our expected value formula to get a lower bound. This sum diverges to infinity. That is, the expected value is infinity. To show this more clearly, we can bound it from below by half the harmonic series. As you typically learn in your first year of university, the sum of 1 on n taken over all positive integers diverges. Therefore, as we sought to prove, the expected value is bounded below by a divergent sum, and so is itself infinite. Imagine the grocery bills. Now it's your turn to prove it. Even though we expect this process to take an unbounded amount of time, show that it will eventually terminate. That is, we are guaranteed that at some point the number of boys will equal the number of girls. That's me done for the day. I'll catch you next time.